Hello, welcome to your lesson on the chi-squared test for independence. This will be video 1. There'll be another video next day. This is at the heart of it, not a difficult topic, but this lesson will be very dense with information, so buckle in and pay close attention. All right, let's begin. Let's say you want to know about the ages of people in your workplace. Of 300 employees, you take a sample of 50. Then we have this. So here's a sample of 50 ages, and we can represent the ages in different ways. Basically, these are called summary statistics, when we have a sample of data and we describe that sample of data. So for example, here we have a histogram showing the ages, we have a mean here, a standard deviation, minimum, quartile 1, median, quartile 3, maximum. These are all things we've talked about. These are all called summary statistics. They summarize a data set. But today we're going to move a little further than just summarizing data. Let's take a look. So what do the statistics of a sample, because this was a sample of 50 taken from 300 employees. So what do these statistics of the sample tell us about the statistics for the entire population? Is this sample, or what we know about this sample, is this enough to say that it's true of the population as well? For example, the sample had a mean age of 30. Is this sample of 50 enough to say that of the 300 that they also have a mean around 30? Well, we don't know, and that's what we're going to look at today. So how can we determine how accurate the sample is at predicting about the population? That's the main question of what we're going to be looking at today and the next few lessons. Okay, so most of the work in statistics as a discipline involves collecting a sample, all right, that's what we just talked about, and from the sample, estimating what are called parameters, which are things like the mean, correlation coefficient, and things like that about the whole population. So again, we have a sample, and from it we make judgments about the entire population. Another kind of judgment we can make about the population is the distribution of it. For example, is the population normally distributed? That's what we looked at in the last unit. So here's the process. We have a population, we want to know some things about it. We take a sample so that we don't have to work with the entire population, because sometimes that's impossible to do. So we take a sample, now we have a sample, and by doing statistics on the sample, we can then make what's called an inference, basically a conclusion on the population. Okay, so this idea of checking parameters from a sample is called hypothesis testing. So let's take a look what this means. In statistics, a hypothesis is a statement about the unknown parameters or features of a data set. So the aim of a statistical test is to try to find out whether the data supports your hypothesis. So we might make a hypothesis. We might have this data from the sample, and then we make a hypothesis or some kind of conclusion we want to make about the whole population, and we're going to run a statistical test to see if the data we have in the sample is actually a valid representation of the population. So we're checking to see if our inference or our conclusions from the sample are good conclusions. That's what hypothesis testing does. All right, so let's say we're running a hypothesis test. We make an initial hypothesis, and we call this the null hypothesis. This is written using typically H sub 0, null hypothesis. And every hypothesis has some alternative hypothesis. This alternative is what will be accepted if the null hypothesis is rejected. And we write the alternative hypothesis as H sub 1. So here's an example. Let's say we wanted to know about the mean of a population. And we are wondering if the mean is actually 20 centimeters. Or is it more than 20? So we could write the null hypothesis as mean equals 20, and the alternate hypothesis as mean is greater than 20. And then we can take a sample and do some testing and see if this is true or not. So let's do this investigation to start. We want to test whether a coin is fair or biased. In other words, does it come up heads, tails 50% of the time, or does it come up with one of them more often than another? That would be a biased coin, one that does not produce a 50-50 chance. So we decide to do an experiment in which we toss the coin 10 times to see what happens. First, we can set the null hypothesis. We can just say, we're going to assume that the coin is fair. In other words, the probability of getting a head is 0.5. Okay, then our alternative hypothesis can be the coin is biased. Therefore, probability of a head is not equal to 0.5. Okay, so we toss the coin 10 times and see how many heads we get. So what number of heads would make you reject the fairness of the coin? In other words, the expectation is 5 heads, 5 tails. So if you get 5 heads, you can say, okay, I think that coin is fair. But what would be your limit? What would be that limit you would set? Like if you got 7 heads, would that be enough to say the coin is biased, or 8 heads? Well, it's tough to say, and it's kind of a matter of judgment, but we're going to look at a way to do this numerically. But for now, let's say we reject the null hypothesis, so we reject the idea that the coin is fair. If the number of heads is 9 or greater, so that means if we get 9 or 10 heads, we're going to say, oh, that must be a biased coin, because to get 9 or 10 heads out of 10 tosses is very unlikely, right? Or on the other end of the spectrum, if we get only 1 head or less than that, which means 0, we're going to say that's also very unlikely, so maybe the coin is biased, right? Okay, so that's what we're going to do for rejection. Now, moving on. So what number of heads would make you suspicious, but not enough to reject the coin as fair? So we said we would say the coin is unfair if this happened. But what about just like, okay, there's kind of that line we're going to draw, and we're going to suspicious, but we'll still say it's fair. Well, if we said we're going to reject it when we get 9 or 10, well then how about saying we will accept that it is a fair coin if h equals 2 or h equals 8, right? So 1 or 9, those were a limit, but 2 is okay. Maybe it's possible you get only 2 heads in 10 tosses, or maybe it's possible you get 8 heads in 10 tosses, but 9 or 10, too much, or 1 or 0, too little. So this could be like our borderline values. Okay, next. Let's find the probability of the heads being 9 or greater, or 1 or less. So this, you may be thinking back, I hope, to binomial distribution. So I'll set up the binomial for you here. We have this binomial, so heads is distributed binomially. We're running 10 trials, 10 tosses of the coin, and we are expecting heads 50% of the time. So running your binomial on your calculator, run one for h is less than or equal to 1. And what do you get as that probability? Well, hopefully you ran a binomial CDF, because we're looking for 1 or less, which means 1 or 0. And it gives us this percent, very small, 0.0107%. Very small chance, 1% chance that would happen. How about the other end? Heads. We get 9 or more heads. It means 9 or 10 heads when we toss that coin. Well, this one you would have to set up like this, because remember, binomial CDF runs from a number and everything below it. So if we're looking for greater than 9, we should do equal to 8 or less than 8, and 1 minus that amount, because that will give us the 9 and 10, which is what we need. So that one, since we have some symmetry here, gives us the same amount, 0.0107. The total then is this number here. When you add those two probabilities, you get that. So the chance of getting a 9 or 10 or a 1 or 0 in terms of heads is this very small chance of about 2%. So very small chance. So I think when we originally selected those numbers as our kind of numbers for rejecting that the coin is fair, that was a good selection, because it's so unlikely that will happen that we can say, if that happens, this coin must be unfair, right? It must be biased. Okay, so looking at that, there's some other significance levels here. So that's what we just calculated as a significance level. So here's the one we had. We said we get 0, 1, 9, or 10 heads. And we found out it was 2.145% chance of that happening. We could also have been more strict with our selection, which is we will reject it if there's 0 or 10 heads, and the chance of that is only 0.195%, even smaller chance that will happen. Or we could have gone more broad with our selections, so 0, 1, 2, and then 8, 9, 10. And the chance of that happening is 10.9% chance. So maybe that would not have been a good selection to reject that the coin is fair, because 10% chance, or almost 11, that's a pretty big chance of something happening. So the chance of that happening is pretty big, therefore we cannot necessarily say the coin is unfair if that does happen, right? Okay, but our original choice of 0, 1, 9, 10 was pretty good. Okay, so do you feel this probability is small enough that you could reject the null hypothesis? Like the one we chose was the middle one. Do you think 2% chance of something happening is enough to say, well, if that happens, then the coin must not be fair? Do you think that's good? Okay, so we were talking about the coin. Let's recap some things. We chose 0, 1, 9, and 10 as being where we reject that the coin is fair. We reject this null hypothesis, the coin is fair. We will reject it if that happens or that happens. And over here, we will accept the null hypothesis. We will accept that the coin is fair. And So we know, let's recap a couple things here. The events for which the null hypothesis is rejected are called the critical region. So these numbers, the 0, 1, 9, 10 that we were looking at, those are called the critical region. And typically a null hypothesis will not be rejected unless the critical region has a probability of under 0.05. In other words, this means that there is only a 5% chance that these events will occur. So we had, again, a 2.51% chance, right? We had, for that, what we selected, it was a 2.15% chance. So that is under 5%. And that's what this says, that typically we do use values of less than 5%. Because if something has a bigger chance than 5%, well, maybe that's pretty likely to happen, and therefore we can't reject what we're testing. Okay, so that, so you know, is called a significance level. So we have a significance level here of 2.15% in our case, because that's what we chose as our critical region right here. Okay, a couple more things. So conceptually, what is meant by the significance level of a hypothesis test? Okay, so here's an answer for that. The significance level of a test describes the probability that the result of a test will fall in the critical region for the null hypothesis to be true. So in other words, again, this 2.15% represents the chance that heads will occur in that critical region, and therefore we can reject the null hypothesis, right? So, and what we mean by for the null hypothesis to be true is because we got those percentages here by using 0.5, the value of what we expect the null hypothesis, right? The 0.5% chance of a head, and we got that percent based on that. So therefore, that there's only a 2.145% chance that that will occur if the coin is fair. Therefore, we can say maybe it's unfair. Okay, next question. Conceptually, we're wondering, what is the purpose of hypothesis testing? So what's the purpose of this kind of testing that we're talking about here? All right, an answer for that could be hypothesis testing allows statistical inferences to be tested for validity. So again, an inference, if we go back to what we saw at the beginning of this video, was some conclusion we make from looking at a sample of data. So let's say we looked at this coin toss, this small experiment of 10 tosses, and we said, okay, well, we only got one head. Therefore, in our small sample, our small experiment, we're going to say, oh, that's so unlikely that we will then reject the null hypothesis, right? So the purpose of this kind of testing is to say, well, are our inferences correct or not? If we are saying this is an unfair coin, are we valid? Is it valid to say that? And if we can argue, yeah, there's only a 2.15% chance of that happening. Therefore, it's pretty valid that we can say now that this coin is unfair. Okay, so with that in mind, we are ready for the next stage. Now that we understand key concepts like the critical region, significance level, and null hypothesis, alternate hypothesis, this is all lead-in to the next topic, which is called the chi-squared test for independence. So please go directly to the next video, which will introduce you to this test of independence. See you soon.